Thanks everyone for joining for another session. Today we're going to be talking about using accurate mass for targeted analysis. That would include things like quantitation and also kind of diving into the suspect screening world as well. So last time, if you were here, Simon spoke a lot about the fundamentals of accurate mass. So if you haven't checked that out, it's on demand now and you can watch it. It's a great watch, especially if you like fish. He talks a lot about fish in it. But I'm just going to reintroduce a couple sort of major fundamentals that I'm going to be speaking about that if you missed it, I don't want you to sort of be lost. The first thing would be mass accuracy. So most of us are probably familiar with this. It's actually a really simple formula. All we're doing is measuring the difference between the observed mass or the accurate mass, what you measured on your instrument, and the exact mass, so that calculated mass. But what's really cool about this is we're doing it so precisely, we're measuring this in parts per million. So for example, in this compound, about 650 Daltons, that equates to 0.0013 Daltons for an error of 2 ppm. So pretty incredible. Usually with a QTOF instrument, that's sort of where we're setting our sort of threshold around 2 ppm, sometimes up to 5, just depending on the instrument you have. The next thing I have to speak to is resolution, right? We're talking about accurate mass. We're talking about high resolution mass spectrometers. So resolution, again, is a pretty easy formula. All that really is going to be is the accurate mass divided by the full width at half maximum. So this is really just a measurement, I like to think of it at least, of how wide your peaks are. So if we think about this, as your resolution increases, your peak width would decrease. So as we move from sort of this nominal mass territory where we have, sort of this wider resolution up to 0.7 Daltons of a triple quad, up to sort of this high resolution mass spectrometry of maybe a QTOF in the 40 and 50,000 range, we get much more defined peaks. And this can be really important when we're trying to sort of distinguish between other compounds. So in the green, you can see this nominal mass spectrum that's kind of hiding the smaller 405 ion that was kind of obscured because of the wide mass range. Whereas with accurate mass, we don't have that problem. But it's one of those things, it's sort of diminishing returns as we kind of go above that 40,000 threshold for what we're actually able to accomplish. The next thing that I just want to reintroduce, because I think this is honestly the most important thing for any sort of high resolution mass spectrometry and I'd argue mass spectrometry in general, is how do we communicate confidence? And confidence is really important when we're sort of relaying these results to maybe a lab manager, maybe a director, maybe we're going to court. How do we communicate how confident we are in what we've observed? And this is something that the metabolomics community tackled and did a really good job defining. They started back in 2004, sort of deciding what do we need to be confident in our results. And then I think a real pivotal time happened in 2014 when Emma Szymanski published her first paper talking about, well, not her first paper, the first paper that she published on this topic of communicating confidence and what pieces of evidence do we need to be confident in our data. And essentially what resulted from that were these tiers. Today, I'm going to be talking about sort of the level 1 and level 2. So a level 1 peak or identification would be something that was confirmed with the reference standard. So that's what we do all the time when we're quantifying, right? When we're sort of doing these quantitative methods, we have reference standards. Obviously, we need a calibration curve. Versus these level 2s that we'll kind of talk about today, which are library matches, where maybe we don't have a standard readily available, but it's something that we are confident in to a certain point. And finally, like I mentioned, the polls are great feedback. A lot of folks asked last time, Simon, some questions about LC method development. Again, if you haven't checked out the nominal mass course, we go into a lot of detail about different parameters for LC development, what column chemistries you should choose, all of that good stuff there. But the one point I would like to bring up here is, since we're talking about sort of these targeted screening or quantification methods, your LC conditions really aren't going to change when doing this approach on an accurate mass instrument. Just like a nominal mass instrument, the more resolution we have, chromatographic resolution, I should say, the better. We want that, right? We want our peaks to be separated when possible. It helps us eliminate things like suppression from the source. Sometimes it's not possible. Just like a triple quadrupole, any sort of QTOF instrument is perfectly capable of handling peaks that are eluting at the same time. So I won't go too far into that, but feel free to ask questions in the Q&A. So now my favorite part. So my favorite part about sort of any high resolution mass spectrometry workflow are the questions it allows us to ask. So there's a lot of different questions we can ask, and it all depends on what you want to use your data for. What's the goal? What's the purpose of your study? Today, we're going to be talking a lot about the question, are these compounds present in my sample? So is atrazine in my sample? Is this specific protein in my sample? Do I see fentanyl in my sample? And if so, how much really? So those are what we refer to as our known knowns, whereas we're also going to talk a little bit about our known unknowns. So our known knowns, known unknowns, and you've maybe heard unknown unknowns. All of this terminology comes from, of course, Donald Rumsfeld, because that is surprising, right? No one really expects that. But it was from a speech he gave a long time ago where he talked about, you know the things you know some things that you don't know, and then you don't know some things you don't know. And for some reason, that's really stuck with the high-res community, and I like it too. And that's sort of some of the terminology you'll hear me use and other folks use. But for those known unknowns, we're asking the question really, I have this list of compounds. Are any of those compounds present? So that can be a really powerful sort of question to ask. And it's something that we think of a lot when we think of high resolution mass spectrometry, QTOF analysis. We think of sort of screening these big databases. And we'll talk about where you can grab those databases, but a lot of times they're things like libraries or spectral libraries. So first, let's talk about this quantitation. So I'm going to be talking about an experiment called an MRM-HR experiment, just sort of to kick off the topic of quantitation. So this would be our sort of highly selective, highly sensitive way to do quantitation on a QTOF instrument. And we're answering that question, are these compounds present? What makes this different from a traditional triple quad? So if we think back to what a triple quad's doing, right? We have an ion that we're selecting. Those ions are making their way into Q1. The ones that we're not selecting are being filtered out. That ion, in this case 215, would then make its way into Q2, or our collision cell. In our collision cell, we have fragmentation. So these fragments are being created. And then just like before in Q3, we're going to go ahead and select for a specific ion. The others will be filtered out, and this ion will make its way through our mass spectrometer. And we're going to measure that MRM. On a QTOF instrument, how is this different? And really, with Q1, nothing's different, right? When we think about QTOF, it's quadrupole time of flight. So we're using our quadrupole in the same way we would on a triple quad. That same ion 215 is making its way into the Q1. The others are being filtered out. Fragmentation is taking place. And those fragments are making their way into the TOF analyzer. And this is where things get a little bit different. So when I describe a TOF analyzer, I typically describe it as a really good stopwatch and a really good measuring tape. And I never say that in front of the R&D team, but that's how I think of it. Over time, we've gotten really good at measuring distance, and we've gotten really good at measuring time. Because of that, and because of the way this analyzer works, one of the things we can do is we can allow all of our ions to pass through this analyzer to our detector. So unlike in our triple quad experiment, where we're selecting for one specific ion, here we have sort of all of the compound's fingerprints. When we think of the way it fragments, right, we kind of think of it, that's the key to its structure. So we have all of that data now that we can use, because the larger ions and the smaller ions are going to take very different times to reach our detector. Great, but how does this differ in terms of setting up a method? So a lot of times I'll get asked when someone's trying to do some of these quantitation methods and they're switching from a triple quad to a time of flight instrument, I don't want to have to redo everything. And that's fair. Method development is fun for a while, and then it's tedious, and then it's just not fun. So I totally understand that, especially if you have thousands of compounds, maybe you're interested in across multiple different methods. And the good news here is that it's really not all that different. So if we take the source portion, so before the ion is introduced, it's made it off of our HPLC, and it's being introduced into our mass spec. Those variables and those conditions are going to be the same, really, between your triple quad and your QTOF. There's not going to be a whole lot different there, provided you're using the same type of source. So let's pretend we're doing electrospray ionization, which probably 95% of us are most of the time. The ion spray voltage, the temperature, those compound dependent parameters that you have to kind of set are all going to be really relatively the same. And things like declustering potential, that energy that we're using to sort of pull the ions of interest into our mass spec, again, it's going to be the same. Those are more dependent on the compound, flow conditions, et cetera. If you want to dive into how to optimize those, all that kind of good stuff, check out the nominal mass series, because we again go into a lot of detail. But based on the poll results, you guys seem to feel pretty comfortable with that, and more concerned about what makes it different. So let's say our ions now have made it through our source. They're either about to be introduced or introduced into our instrument. What other variables are there, and what do I need to optimize for? So if you're familiar, at least with SCIEX triple quads, you'll have things like your declustering potential, your collision energy, even your CXP, so your collision cell exit potential. For declustering potential, right, that's just the energy that we're using to pull those ions into our mass spectrometer. Again, that's going to be dependent on what compound you're looking at. So there's not going to be a whole lot of difference there. Same thing with collision energy, right? That's the energy we're using to fragment our compound in the collision cell. Up until this point, that energy is going to be basically the same. Obviously, disclaimer, there's some variability as you go between instruments, of course. But in terms of re-optimizing, usually most folks are pretty happy with their sensitivity and don't have to sort of redo that portion. And then CXP, or collision cell exit potential, something we normally don't optimize on a QTOF simply because it doesn't really make much of a difference. Similar to a triple quadrupole, it's something that you're not really gaining a lot of sensitivity from when you're optimizing for a specific compound, maybe 1-2%, not a whole lot. So just to kind of summarize, when we think about all those source conditions on a triple quadrupole, we're doing all the same things. Those variables should be very similar, if not identical, to what we're doing on a QTOF instrument. So GS1, temperature, ion spray voltage, all of that is going to remain pretty much the same, if not the same. And the same with compound dependent parameters. So collision energy, declustering potential, all those variables are still the same thing we're going to optimize for. So up until this point, there's not a whole lot of difference, right? When we think about how we're going to set this method up and what we're doing. Because the end goal, right, is quantitation. So we're running some standards, and the reason we're running these standards is to build a calibration curve, right, which is just the area of response to the known concentration. So we can figure out, hey, I have this unknown. What is its concentration? That's really the question I'm asking is this compound here? And if so, at how much? So what makes quantitation different on an accurate mass system compared to a nominal mass system? And that's really, as you would guess, the accurate mass. So here I have a spectrum from a nominal mass instrument where we're isolating for a specific ion. So we said, hey, look for this 284 ion. Do you see it? And we're at this point doing no fragmentation. So we're just looking for a parent mass. And what you see is a really noisy spectrum. And there are a lot of peaks here. Our peak of interest is here, but I couldn't tell you what what it is. I couldn't tell you which one of these peaks it was. I might think maybe the 1.5 minute retention time peak, maybe, but I obviously wouldn't be very confident. I would be 0% confident that that truly was it without a standard. But when I compare that same data on an accurate mass system, all of a sudden it becomes very obvious which peak is my peak of interest, right? Because we were able to use sort of go down to that fourth decimal place of 0.0001 Daltons, we now can really see through all that noise. The way I kind of like to describe accurate mass and nominal mass is with nominal mass, it's kind of like standing on a bluff and looking out over over a forest. There's plenty of trees, and we could kind of see what we're looking at. But when we use accurate mass, it's like going into the forest and looking at a specific tree of interest. So really zooming into our data. But that's just our QTOF MS or apparent mass. So yeah, you could definitely quantify, build a calibration from that parent mass, and then figure out what the concentration is in your standards, or I'm sorry, you should know that in your unknowns. But what happens when that isn't enough? So one thing I get asked about is why would you use MS data for quantitation? And really it's the same reason we use it for nominal mass quantitation, the ability to be more specific and have more confidence. So here I have an example of a pesticide that I was looking for in cannabis. So I had this cannabis that I knew didn't contain this pesticide, and I was doing some method development. So I've got my two compounds of interest here in my standard. They look great. I'm happy with them. But then when I ran my matrix blank, I was concerned because when looking at the MS1 data, I see, there's these two interferences. And when I spiked in my standard, even worse news, they come out at basically the same time. There's no chromatographic resolution between these peaks, which would make quantitation basically impossible. I wouldn't be very confident in this value at all, right? Because I'm sort of having to draw one of the dreaded foots, as I call them, where we're not truly defining our peak of interest. So that's bad news. But what can I do to sort of avoid this? And what I did was use MS data. So that compound had the same mass as my compound of interest, but it didn't have the same fragmentation, right? So all of those fragments are like the compound's fingerprint. And when I used a fragment to do my quantitation on this compound, all of a sudden my matrix blank is clean. I don't see that sort of interference. I have zero concern that this is my peak of interest now in my spike sample, and I can be highly quantitative and figure out exactly how much is in my sample. So that's great. That adds confidence, and confidence is really important when talking about data quality. So if we kind of take a step back and think about what data we have to be confident with in nominal mass, we have things like the MS data, like I just said, which is something we have on a QTOF, which is great. We have our retention time, still really important, right? We use that to be, again, confident that this is our compound of interest. And we have things like ion ratio. So we know the difference between a quantifier and a qualifier ion. We can get a ratio of that and be pretty sure, yes, this is what I'm looking at. That being said, I think almost all of us have been in a situation where we have all these pieces of evidence and there's still something kind of telling us that something's not right. Maybe the retention time is slightly off, but it's still within your accepted window. Maybe the ion ratio is just a little confusing. It's within that 20% tolerance that you set, but it's unlike any of the other ions you've seen or your standards, and you're just a little concerned. With a nominal mass instrument, that's where you're at. Unfortunately, you'd have to use some sort of orthogonal approach to try to figure out, yes, is this truly a positive or is this just a false positive? There's not a whole lot more data you can use to be confident. compared to an accurate mass system where without having to do anything, you have all of this other evidence. We have that mass error like we've been talking about. We have that mass error not only on the parent, but we have that mass error on the fragment as well. So we've got two pieces of information there. We have that library match. So that library match, I'm going to talk a lot more about library matching in a couple slides, but we can think of it for the purposes of this as sort of that compound's fingerprint. And we have that isotope ratio. So Simon spent a lot of time talking about what an isotope ratio is, but essentially we have the chemical formula and we're seeing if that MS1 data makes sense. Does that isotope ratio line up? And I have this real example of using all those pieces of data. So this was actually part of a project I'm working on where I've collected a bunch of supplements and drugs from gas stations and other over-the-counter sources, and just screening them and seeing what is present in them. And here we have a natural product, and I wanted to know how much of this product was present in this supplement. So I went through and used my pieces of evidence, and I said, okay, the mass error, that makes sense for both the fragment and the parent. The retention time makes sense to my standard. I'm confident there. The fragmentation all matched not only my standard, but my library. So I can sleep well. I've got my ion ratio still, so I can still compare the ratio of those fragments if I needed to. And then I have my isotope ratio. So the formula makes sense for what I'm seeing in my MS1 spectrum. So now I'm incredibly confident. There's really not a lot of room for me to be not confident that this, yes, is indeed my compound of interest. And the goal here, right, the question I was asking was how much. So I can just go ahead and quantify this supplement and say, yep, there's 12 parts per trillion in this supplement. So that's great. Quantitation on sort of these accurate mass instruments isn't too much different. Really, all you're doing is adding these really key pieces of evidence to be confident in my result. But what if you wanted to ask a different question? So still kind of falling within this sort of targeted analysis, it really depends on which community you hang out with. I mostly hang out with the environmental community. So we really distinguish sort of the targeted analysis from suspect screening, but there can be sort of this intermingled gray area. So that's why we thought it would be good to include it in this session. So for suspect screening, we're asking that question, are any of these compounds from a defined list present? So that can be really powerful, right? In that previous example, I showed you a compound that I found in a supplement. And I was specifically looking for this compound because I knew it was there. It said it in the ingredients, this compound is present. But my real goal for this study was to see what else was there. And I have a list of these drugs that I would like to look for. I don't have standards for them yet, but I want to know if they're there, and I want to sort of justify me purchasing, a bunch of these standards. So how do I do that? And this is where things get kind of cool, right? Because we know there's going to be so many compounds present in this sample. How could I possibly collect MS data on these if I don't know what I'm looking for, the retention time, all these sort of variables? What kind of technique can I use to acquire that data? And there's a few options, but the first thing we're going to do is we're going to do a TOF-MS scan. So this is going to be our experiment number 1, or MS1 as sometimes it's referred to. And here, what this looks like on a QTOF instrument is we're letting all our ions pass through Q1. Nothing's occurring. We're not filtering anything out. They're passing through Q2 as well without fragmenting. And then they're making their way into the TOF analyzer where we're measuring the parent mass. So we're getting a good idea about what the compound of interest's parent mass was. And again, because these masses are, so different. When I say so different, I'm talking about 0.0001 Daltons different. They take different times to reach that detector, so we can distinguish between them. But what about that MS data? So there are two methods that I'm going to discuss when acquiring MS data: data-dependent acquisition and data-independent acquisition. So If you're a SCIEX user, data-dependent acquisition, we sometimes refer to as IDA or information-dependent acquisition, and this can get kind of confusing, and admittedly so, especially as you communicate maybe with colleagues that are using different vendors' instruments, what is actually occurring here. So what I would suggest is that you figure out what bucket the experiment you are doing falls into, and that usually helps. So are you using a piece of information to conduct an MSMS experiment, or are you using no information? Within there's obviously nuances. I'll just speak to the SCIEX perspective of what we do, but that's sort of the two buckets that MSMS data falls into when acquiring in sort of this kind of fashion. So for data-dependent acquisition, which I'll go through first, we are using a piece of information. So we're saying, hey, do that TOF-MS scan. Then if any of the ions in that scan meet this criteria, do an MSMS experiment. And that criteria can really depend on what the goals of your study are. Sometimes that will be set to things like neutral loss. Do you see this neutral loss in the survey spectrum? Do you see a certain isotopic ratio? Maybe you're looking only for chlorinated things. That's a pretty specific isotopic ratio, and you want to only collect MSMS data on those things. Or what most commonly is used, and honestly, probably 99% of the time, is an intensity. If this compound is above a certain intensity, then I want you to fragment it. I want you to perform some sort of MSMS experiment on it. So here I've got my survey spectrum, and I'm setting my intensity threshold. And I'm saying, hey, anything above this 3.5 e⁵ line, I want to fragment. So the top 10 to 12 peaks above this line, go ahead and do MSMS analysis on them. And the instrument will go ahead and do that. So I haven't selected these ions. I haven't given it really any information aside from an intensity threshold to choose these things, right? And if we think about the question we're again asking, are these compounds present? We couldn't possibly set up an experiment with, let's say we're searching a library of 1,000 different drugs, 1,000 different MRM HR experiments. It would just be too many. They'd be running all the time since we didn't know when the retention time was. So instead, this is our way to sort of create a comprehensive MSMS approach that doesn't rely on things like retention time. But what if you're worried? And each one of these techniques has its sort of areas it shines. And what if you're worried that maybe you're going to miss something? So maybe you're worried that, hey, I saw you say the top 10 to 12. What if it's not in the top 10 to 12? Or what if you're having trouble picking an actual intensity threshold? You're worried you're going to miss something that's really important. And that's where these data-independent acquisition approaches come into play. So for us, I'll talk about SWATH. So SWATH, sequential window fragmentation of all theoretical fragments. Only time I'll say that is basically what I like to think of this sliding window. So this window is being moved through our mass range, and it's going to go through the entire mass range. And that means that you're not going to miss any of this data, but that can kind of be hard to conceptualize, I think. So we have our mass range here. We've got a mass range from 100 to 500 Daltons, or M/Z, I should say. So what we're going to do with SWATH is we're going to go ahead and say anything within my first sort of window. In this case, my window is from 100 to 120 M/Z. I'm going to allow to pass through my Q1, be fragmented in my Q2, and then make its way to my TOF analyzer. Anything in my next experiment, so moving on, anything from 120 to 140 is going to be here. So in this experiment, anything that falls within that range is going to go ahead, make its way through Q1, fragment at Q2, and make its way to our TOF analyzer, and so on and so forth. So the amount of windows you have and the width of those windows is really going to depend on what type of analysis you're trying to do. So we don't have to sort of set those windows at a defined mass range. A lot of times I'm doing small molecule work, and typically, let's say I don't see anything above 500 Daltons 99% of the time. I don't want to spend a lot of effort collecting data, MSMS data on things larger than that. But I also don't want to miss anything just in case there's this one chance that there might be something there. So I can set a really wide range from, let's say, 500 to 800. So maybe that window's 100 Daltons or 300 Daltons, and have really tight windows in the area where I have a lot of compounds that I'm interested in. So it gives you some flexibility there. But all in all, as kind of like a review of what these things are doing, if we are going to collect all of the MSMS data, we'd be fragmenting everything at the same time, which is great. You're not going to miss anything. Downside is it's very complicated. You have a lot of overlapping things. Obviously, we saw how many things elute at a certain time. All of that data would be overlapped, and it could be really, really confusing to work through. With SWATH, same idea. We're not missing anything. We're collecting MSMS data on everything. There is the chance that there might be something within that 100 to 120 window that happens to elute at exactly the same time. Luckily, our software has gotten really good at figuring out whether that peak's fragments belong to this peak or that peak, just using some principal component analysis. But we're not missing anything is the big key. Compared that to our data-dependent acquisition, or if you're a SCIEX user, you'll see it in the software as IDA. That is very similar to MRMHR in the fact that we are collecting data on just one specific ion all of the time. And that means that there are sort of these areas where these sort of methods shine. One I always like to bring up is data archival. So with something like SWATH or a data independent acquisition approach, all of that MSMS data is always there, compared to a data dependent acquisition approach where maybe something was missed. It happens, right? The example I like to give is when I was in grad school, Simon and I actually from the last session, along with another group, went ahead and characterized a whole bunch of these HRMS samples, which are these firefighting foams that contain a bunch of fluorinated compounds, so PFAS. And we were looking for new PFAS compounds. That was the question that we were trying to sort of answer. And we ended up finding a couple hundred of these PFAS compounds that were previously not discovered. And we collected that data using SWATH, and it lived on a hard drive for 4 or 5 years. And then a graduate student came in and they had a different question. She was asking, what hydrocarbon surfactants are present in those kind of solutions? And because we collected the data using this sort of data independent acquisition approach, she was able to go through and create a suspect list of hydrocarbon surfactants and identify if they're there. So that can be really powerful. If you wanted to do things like, let's say, quantitation, as we discussed before, you can just go ahead and use either of these approaches. So we're using that MSMS data in the same way. So we don't have to worry about whether or not, it's SWATH or IDA. It's going to be highly quantitative either way. The only difference between the MRM experiment I showed earlier is there we can actually optimize for a certain collision energy. Here, since we aren't sure what we're going to see, we have our known unknowns. We don't have those optimal collision energies for the utmost sensitivity. And finally, something like library building. That's a place where information-dependent acquisition or data-dependent acquisition really shines because we're really confident that we're collecting data on just that one specific ion. But what does the suspect look like? What are we doing? So really, a suspect list in its simplest form just needs to contain a list of masses. These masses, hopefully, would be from a formula. But they don't have to be. It would just be helpful because then we can use those things like isotopic information to get an idea of if this is truly my compound. But in reality, it just needs to be a list of masses. And those masses can come from a variety of different sources. Probably the most common are spectral libraries. But you can use things like the Norman suspect list exchange. You could create a list of potential metabolites that you think you might see where you don't have that spectral information. You take that mass or formula and you put it into a components table like this, and you would essentially rely on your peak picking software, so here SCIEX, to go ahead and say, do you see this compound? I don't know its retention time, but is it present? And our peak picking softwares and algorithms have really improved since I've started my spectrometry, and do a really good job at this sort of complex ask of, is this here? So where can I find these spectral libraries to make lists from? They exist in a lot of different places, and each have sort of positives and negatives. So you could go ahead and purchase a library from someone like us at SCIEX and grab a NIST library or maybe a forensics library. There's a lot of pluses in that we'll talk about. That would mean things like it was collected on a similar instrument that you have, et cetera. But there are also these incredible open source libraries that exist. Things like Mass Bank of North America, MONA, is a great example of a user-created library that is extremely extensive. Downside is sometimes it'll be collected on maybe a different instrument than you have under conditions that maybe aren't optimal for what you're trying to achieve. And regardless of which one you choose, you kind of need some criteria to understand if it's a good match. How can I possibly sort of judge this? And that's where sort of the scoring metric comes into libraries. So there are really three major ways to score how good of a fit this is. This is something that we really don't ever have to deal with when we're talking about nominal mass MRM style workflows. But if you maybe came from the GCMS world first, you'll probably be kind of familiar with this terminology. So the sort of most stringent, I would say, way to score your match would be using something called a purity score. So a purity score is really, really good to make sure you don't have any false positives, but you may end up with things like false negatives. And the reason being is it's saying anything in your spectra must match the spectra in the library. So there shouldn't be any extra peaks. There shouldn't be any missing peaks. If they are, or if that happens, I'm going to go ahead and penalize your score. If you're collecting data on let's say you have an X500 and you're using a SCIEX library, well, purity is a really good option for you because that data was collected in a very specific way to how you run your X500 most likely. So you should have really nice purity scores. However, if you're searching against something like MONA, maybe they used a much, much higher collision energy. So there's a lot of smaller fragments, but it's missing some of the bigger ones. Your purity score is probably going to be pretty low. So that might not be a good option for you. Versus something like a fit score. So a fit score is really good at having low false negatives, but you might end up with some false positives. And the way I like to think of a sort of a fit score is any extra sort of fragments that are in your unknown aren't going to be penalized if they're not in your library spectrum. So this is good if it was acquired sort of under these different conditions. Again, maybe you have collected the data in a way that you have high collision energy, you have a lot of these smaller fragments that are present in the spectrum. It's not going to penalize your score, but it still wants all of those sort of diagnostic key ions that were in the library spectrum to be present, which is different than your first fit. And this is your last one. So I always think of kind of fit scores, taking your unknown spectra, comparing it to your library. A reverse fit is doing the opposite, is taking your library spectrum and comparing it to your compound or what you observed. This is great for a couple things. Making sure a library is actually what you should be using. So maybe you tried out a spectral library from MONA. This is a good way to assess if this is a good library for you to be querying against with maybe some known standards. And it basically is just a complement to the fit score. So any spectra that, or I'm sorry, any fragments that are present in your library score that aren't present in your acquired spectra aren't going to get penalized. The last sort of thing I think is really important to discuss when talking about any sort of library searching are these thresholds, these intensity thresholds of your fragment. So you can imagine you have all of these fragments present. But what about the ratio? When we think about nominal mass, we talk a lot about ion ratio. How does this work with library matching? And it depends, again. If the conditions, let's say you have an in-house library that you've acquired standards, and now you're querying a data set, you can set the intensity threshold, so the difference between the intensity of your observed and your library spectrum, pretty close. There shouldn't be that much variation provided you're using the same collision energy, et cetera. It doesn't really matter what the concentration is. It's more so what are the conditions you acquired the data with. However, obviously, if you're using maybe a spectral library that was made computationally, so it doesn't have any intensity data, it just knows these fragments could exist. Or maybe you took one from one of your colleagues who's using a very different instrument and using a very different collision energy. Can you still use that data? And you can, you just have to set those intensity thresholds much higher so that you're seeing is the peak there, but you're not necessarily caring if it's a good match in terms of the ratio of that intensity. So how does it look when I use this data? Very similar, right? I just have less pieces of evidence for me to be confident with. I still have my mass error. I have, in this case, I'm doing a library match. So I have my mass error for my parent, for my fragments. So I can be really confident there. I have my isotopic information, again, because I'm matching to a library. So I have some structural information likely too. But I certainly know my formula, so I can do that isotopic information. And then I have that MSMS library match. So I'm still very confident, but you notice, obviously, with a suspect list, I'd be missing things like retention time. I wouldn't get that until I ran a standard on my instrument. So where does this come into play? And it's an example I like to use. So I've got two drugs here. I've got tramadol and ODV. And what you notice is they have the same mass. They have the same mass, they have the same formula. So I'm in a tough spot. When I initially do my suspects list screening, I notice, my tramadol and my ODV, they have terrible matching for purity. I acquired this data on my own instrument. This shouldn't be the case. I shouldn't be experiencing this. I don't think this is the compound. I think it is. And in this case, yes, it's obviously not. So all I needed to do here was just go ahead and swap those. Since they had the same paramass and we didn't know a retention time, it was pretty tricky. But when we swap those, we see, now the library score makes a lot of sense. It's basically 100. I can be really confident in the data I'm observing. So using those pieces of evidence to sort of get to a point where you feel good. Now we're at that level 2 that we talked about in the Szymanski index. To get to that level 1, obviously we need to run a standard, but still a library match like this gives us a lot of confidence and certainly more than justifies purchasing that standard if we don't have it already to run. And finally, I'm going to be going in pretty deep next session into the non-target portion. And a lot of this will get explained in much more detail. But when it comes to non-target, when it comes to suspect list screening and you don't have a library, let's say there's just not one available, I can make a list from a lot of different compounds, right? I could grab a list from PubChem. Maybe these are theoretical things that should exist. How can I then score it or be confident in my results if I don't have spectral data to sort of say, yes, this is a good match? And there are a lot of really cool tools that you can use that I'll show you next session, since it kind of falls into the non-target world a little bit more than the suspect screening world usually. But these tools all sort of rely on different sort of approaches. So most of them, I kind of just listed my favorite open source ones here. Things like MetFrag, SCIEX, CSI Finger ID are using some sort of logic to figure out, is this a good match or not? And the one I really like and I recommend to folks that's open source is this tool called SCIEX. It was created in a it's really cool. It's really slick. What they did basically was feed a bunch of spectral data to an algorithm and have it learn. So it did some machine learning to say, if this structure created this fragmentation, then if this fragmentation exists, so it's taking some unknown fragmentation, it says the structure likely makes sense that it's this. So this can be really powerful. I use it all the time for searching things like big databases like PubChem, where I want to say, hey, is this present or not? And again, we'll go into a lot more detail about what's actually happening with some of these next time. And we'll also talk about the tools that we have here at SCIEX that you can use that are readily available. But just to sort of wrap this up and get into what we accomplished or what we talked about, we're really sort of talking about two questions. The first question we're talking about is, are these compounds present? And can you answer that question and be quantitative using accurate mass? And you can. In fact, I would argue it's a little bit easier to do it with accurate mass because you have all of these pieces of evidence that say, yes, I am confident in my results. I have now mass accuracy. I have my isotopic information. I have this library match. So I'm very, very confident that this is the compound of interest. I've still got that MS data, so I can get rid of some of that noise. So really, we're adding the ability to remove noise, and we're adding the ability to be confident or more confident in our data set. So that's awesome. I think everybody enjoys being confident in what they present. And then also we talked about the question, are these compounds present from this list? And can we answer that question with accurate mass? And yes, obviously, I think that's kind of an area that when we think of accurate mass, we think of this question. This is probably the most common question that folks are trying to answer when they first think about why would I use accurate mass. It's for this question, do some library searching. I have this unknown sort of supplement. I want to see if these drugs are present, et cetera. And a QTOF does a great job of that, right? Because we can acquire MS data quickly without designating sort of what parent ion, whether you're using data independent or data dependent acquisition, depending on what you're trying to accomplish. You can get at, are these compounds actually present in my sample? But if you want to answer that more complex question of what is in my sample, are these samples the same? What makes them different? Please join me for the next session, which is my favorite topic in high resolution mass spectrometry, non-target analysis. We're really going to dive into how to answer some of those really complex questions and what tools are available for you to use. And with that, I'd be happy to take any questions.